So the rest of 3.3 is just finding the intervals where a graph is concave up, concave down, and the inflection points. And I typed up on my sheets what steps I need to do just so I don't have to write them down every time. But it's just the same as the first and second derivative tests, so hopefully these come easy to you. So 16, I'm going to go through all the business to figure out where the graph is concave up and concave down. I'm going to find the first derivative. It's not part of my answer, but I need it. First derivative is 6x squared minus 12x. And then I'm going to do the derivative of that to get the second derivative. This isn't even asked for in terms of the intervals, but I'm going to need it too. So this is going to be 12x minus 12. I need to have the second derivative to answer where the graph is concave up and concave down, but it's just not asked for as for part of the question. Now I'm going to get the critical numbers by taking 12x minus 12, setting it equal to 0. I'll add 12 to both sides and get 12x equals to 12, and then I'll divide both sides by 12 and get x equal to 1. In section 3.1, I asked for these as part of the homework. Here, for some reason, I didn't ask for them. I'm not sure why, but I didn't. Now I'm going to take the number that I found, plug it on a number line that also includes negative and positive infinity, create intervals that only have round parentheses, the interval from negative infinity to 1, the interval from 1 to infinity. Then in each region, I'm going to pick a number. In the first region, I'm going to pick 0 because it's in that region, and 0 is my favorite number to pick generally. And in the second region, I'm going to pick 2. And I'm going to plug them into the derivative. I'm going to do second derivative. I'm going to do f double prime of 0 is 12 times 0 minus 12. And f double prime of 2 is 12 times 2 minus 12. This one comes out to negative 12. This one comes out to positive 12. In the first region, because it came out negative, doesn't mean the graph is decreasing, but the graph is concave down. In the second region, because it came out positive, the graph is concave up. So my answer to 16a, the graph is concave up in the interval from 1 to infinity. My answer to 16b, the graph is concave down in the interval from negative infinity to positive 1. And then for part C, because the graph changes concavity at 1 and the 1's in the domain of the function, that 1 is the x-coordinate of inflection point. I need to get the y-coordinate of the inflection point, so I'm going to go y equals, and I'm going to use the original function and do 2 times 1 cubed minus 6 times 1 squared plus 5. This is going to be 2 minus 6 plus 5 because the 1 piece is just turned to 1. That's going to be 1 if I do it right. So the inflection point is going to be the point 1, 1. So that's kind of everything. I even shaved off some of the stuff that I have typed, but this is the bulk of what we need. If we can just find the second derivative, get its critical numbers, create a number line, create intervals, plug numbers into the second derivative. If it's negative, that whole interval is concave down. If it's positive, that whole interval is concave up. If the graph switches concavity at a value of x, that's the x-coordinate of an inflection point. I need to get the y-coordinate of the inflection point by using the original function. Let us do 17 together. Again, dangerous because I don't have the answer written, but let's do it. So for 17, just to steal some of your homework, let me do the second derivative for 17, but first I need the first derivative. The first derivative for 17, I'm going to bring the 3 and multiply it by the coefficient of minus 1 and get negative 3x squared because there's an implied coefficient of minus 1. And then the second piece is going to be minus 6x. That's the first derivative. Now I'm going to write down the second derivative. I'm going to go 2 times minus 3 and get minus 6. Pick up my x. But then the derivative of minus 6x is minus 6. Done with the second derivative. Now I'm going to set it equal to 0 to get my critical numbers. You'll see that the critical numbers, I always like to make them nice integers. I don't like fractions if I can avoid it. And I like small numbers. So I took the second derivative, set it equal to 0, added 6 to both sides, and then divided by 6. Got the same critical number of 1. I think consistently we'll get 1 and 0 for critical numbers in this section. Just keeps the numbers easier to work with. Now I'm going to plot those critical numbers, or that critical number, on a number line that contains the infinities. I'm going to create intervals, the interval from negative infinity to positive 1, the interval from positive 1 to infinity. I'm going to pick a number to plug in. In the first interval, I'm going to plug in 0. In the second interval, I'm going to plug in 2. Just because 0 is an easy number and it's in the first interval, 2 was right at the edge of the second interval, so it's probably easier to do the math with. Now I'm going to plug those into the second derivative. I'm going to do s double prime evaluated at 0, which is going to be 6 times 0 minus 6. That's going to be negative 6. And then f double prime evaluated at 2, that's 6 times 2 minus 6. That's going to be positive 6. Anytime I get a negative result, the graph is concave down in that integral. And anytime I get a positive result, the graph is concave up in that interval. So the first interval is concave down, the second interval, the graph is concave up. The graph changes concavity, and 1 is not an asymptote, so that's going to be the x-coordinate of an inflection point. So for part A of 17, the graph is concave up in the interval from 1 to infinity. For B of 17, the graph is concave down from negative infinity to 1. And for C of 17, the x-coordinate of the inflection point is 1. To get the y-coordinate, I have to do this. I have to think of the function probably as negative 1x cubed minus 3x squared plus 5. And then plug 1 in. Go negative 1 times 1 cubed minus 3 times 1 squared plus 5. And do this on your calculator. I'm probably dumb doing it in my head, because this is when I start to write down mistakes, but I think this comes out to positive 1 again. So I think the inflection point is going to be 1, 1. Let me do this on my calculator real quickly. Negative 1 times 1 cubed minus 3 times 1 squared plus 5. It is 1. And that's everything for 17. When we have fourth powers, we probably get 2 critical values and 2 inflection points. That's probably what's going to come up with 20. This is probably one of those W-type graphs. So let me do the work. Notice I'm not graphing this because I'm trying to keep students from cheating. So many students will just look at a graph and make up answers without doing the calculus. So I'm trying to avoid that as long as I can. So let me find the second derivative in 20. In 20, the first derivative, I bring down the 4, put it in front of the x and get a 4x cubed. And then 2 times minus 12 is minus 24. And then I get an x. Second derivative is what I need for concavity. My second derivative, I go 3 times 4 is 12, lower the exponent by 1. And then minus 20, oh boy, minus 24x gives me minus 24. This is troubling. Really? I think I have a mistake on my answer. 4x cubed minus 24x. Let me change this problem. Otherwise, the math is going to be ridiculous. Let me change it to have the same minus 6x squared as yours. Let me change this, sorry, to x to the 4th minus 6x squared minus 3. I was being dumb. I have a mistake on my key, but this will fix most of my mistake anyways. Sorry. I was going to start getting square roots for the x coordinates of the intervals, and that I don't want that. So let me redo this with this new problem and dump out that problem. I'm going to get first derivative is 4x cubed minus 12x. Second derivative is 12x squared minus 12, much better. Now, I am going to find the critical numbers by setting the second derivative and setting it equal to 0. I'll go 12x squared minus 12 equals 0. Pull out a common factor of 12 and get 12 times x squared minus 1 equals 0. Factor the x squared minus 1 into x plus 1 times x minus 1. And then set the individual factors equal to 0. The factor of 12, because it doesn't have an x, won't give a critical number. The factor of x plus 1, I would minus 1 from both sides and get a critical number of negative 1. The factor of x minus 1, when I set it equal to 0 and add 1 to both sides, I'll get a critical number of positive 1. So for my number line, I'm going to have negative infinity on the far left edge, positive infinity on the far right edge, and then negative 1 first, followed by positive 1 second. And I'm going to create my intervals. I'm going to do an interval from negative infinity to negative 1, an interval from negative 1 to positive 1, and an interval from positive 1 to infinity. And now I'm picking numbers. In my first interval, I'm going to pick negative 2. My second interval, I'm going to pick 0. My third interval, I'm going to pick 2. Always pick 0 unless it's a fraction, and pick numbers right close to the edges. So first interval, x equal to negative 2. Middle interval, x equal to 0. Third interval, x equal to 2. Plug them into probably that version of the second derivative. So I'm going to go 12 times negative 2 squared minus 12, and 12 times 0 squared minus 12, and 12 times positive 2 squared minus 12. First one, 12 times negative 2 squared minus 12 is 36. Middle one's just going to be negative 12 because the first piece is going to be 0. And the second one I could do in my head now because it's going to be the same as the first, because negative 2 squared is 4. It's the same as that. So I have my y's. First interval concave up because of the positive result. Middle interval concave down because of the negative result. Last interval concave up because of the positive result. So my answer to part A, this graph is concave up in the interval negative infinity to negative 1, and then again the interval from 1 to infinity. Part B, the graph is concave down in the interval from negative 1 to 1. So I go concave up, concave down, concave up. So in both critical numbers, the graph changes concavity. They're both the x coordinates of inflection points. So for part C, I'm going to get two separate inflection points, and they don't have to have the same value of y. The first inflection point has an x coordinate of negative 1. The second inflection point has an x coordinate of positive 1. I'm going to use this original function that I've recreated. So for the first one, I'm going to get y equals negative 1 to the 4th minus 6 times negative 1 squared minus 3 for the y coordinate of the first inflection point. For the second one, I'm going to do y equals 1 to the 4th minus 6 times 1 squared minus 3. And I think I'm going to get the same results because when the negatives turn to the same number as a positive, but that doesn't matter. I can do this on my calculator. So negative 1 to the 4th minus 6 times negative 1 squared minus 3. The first point is going to be the inflection point of x equal to negative 1, y equal to negative 8. And the second one I think is going to be the same. 1 to the 4th minus 6 times 1 squared minus 3. I also get negative 8. So hopefully this isn't really humbling. It's really exactly the same as what we've done for increasing and decreasing maximums and mins, except we're just attaching different words to the results. But the taking the derivative, setting them equal to 0, creating my number lines, checking critical numbers, it's all the same. It's just interpreting them. Instead of a negative meaning decreasing, it means concave down. Instead of a positive meaning increase, it means concave up. But hardly that different. I am shocked that I don't have the derivatives written down here, but let me push through them. So we have to do an E problem, and normally if I have a second derivative required for an E, I just give it to you. On the test, I wouldn't have you do the second derivative. Let's do 21 together. I don't think I do a second derivative with an E on the test. I do first derivative with an E, I know that, but I don't think I do a second derivative problem with an E. So first derivative, ugh. I need the first factor, which is 2x, the second factor, which is e to the x, then the derivative of the first factor, which is 2. The derivative of e to the x is e to the x. It's cheating and saving some time. So my first derivative is going to be 2x e to the x plus 2e to the x. Can factor out a 2e to the x and be left with x plus 1. Fast, but I will give this to you if I would do something this horrible on a test. Now we move on to the second derivative. Product rule again. Second derivative, first factor is 2e to the x. And I'm just going to write its derivative down because I want to save some time to get to the fraction. You can do this derivative manually following the steps we learned in the last chapter if you care to. My second factor is x plus 1, and its derivative is just 1. It's just the coefficient of the x term. So cross multiply, cross multiply. Second derivative is cross multiplying this way. 2e to the x times 1 is just 2e to the x, plus cross multiply this way. It's 2e to the x times x plus 1. I'm not going to multiply that out. I'm going to factor out this 2e to the x right off the bat. And I'm going to say second derivative, my lord, is 2e to the x, parentheses, this first e to the x turns to 1, the second e to the x turns to 1. And this gives me 1 plus x plus 1 inside my parentheses. So for problem 21, your homework problem, the second derivative is 2e to the x times x plus 2. I 100%, if I asked the second derivative question with an e function like this, I would give you this on the test. So now I have the original function and the second derivative. The second derivative is going to be 2e to the x times x plus 2. I'm going to move on and find my critical numbers. Find the critical numbers by taking the second derivative and setting it equal to 0. So I'm going to do 2e to the x times x plus 2 equal to 0. That'll cause me to go 2e to the x equals 0 and x plus 2 equal to 0. And e to the power can never be 0, so 2e to the x equal to 0 doesn't give a solution. And for the x plus 2, I'm going to minus 2 from both sides and get the only critical number as negative 2. Now I'm going to create my number line, put negative infinity on the far left edge, positive infinity on the far right edge, my critical number of negative 2 between the infinities, make an interval from negative infinity to negative 2, and an interval from negative 2 to infinity. The first interval I'm going to plug in -3. The second interval I'm going to plug in 0. So x equals -3, x equal to 0. Plug it probably right into there. So for the first number, -3, I'm going to go the second derivative evaluated at -3 as 2e to the -3 times -3 plus 2. I'm going to do that on my calculator. For the second one, I'm going to go with the second derivative evaluated at 0 as 2e to the 0 times 0 plus 2. This one comes out to 4. I'll do them both on my calculator. So 2 second and ln e to the -3 times -3 plus 2. And I get negative, doesn't matter, -0.09957. It's negative. That's the important part. So the graph is concave down in that region. Second region, 2 second ln e to the 0 times 0 plus 2. I get 4, which means the graph is concave up in that region. So for 21a, the graph is concave up in the interval from -2 to infinity. For 21b, the graph is concave down in the interval from -infinity to -2. The graph changes concavity and it's continuous there. So for 21c, I have an inflection point and its y-coordinate is -2. Its x-coordinate is -2. I need to get its y-coordinate. And in 22, I'm just going to plug this into the original function. I'm going to get y equals 2 times -2 e to the -2 power. That's going to give me y equals -4 e to the -2 power. I'm going to make that negative exponent positive by creating a fraction and moving the e down to the denominator of that fraction. So the y-coordinate of my inflection point is -4 over e squared. That's maybe a bit much, I guess, for a Math 212 class. Maybe not a bit much for a Math 220 class. Last problem. Should be able to do it in 8 minutes because it's bad, but I give us the derivatives. I had a printer malfunction, and the derivative got cut off a little bit, but I think it's all good enough. I think the original function in problem 24 is this, and the second derivative is that. That's going to happen on the test. If a second derivative is ridiculous like that last second derivative, I'm just going to give you the second derivative. So I'm not going to worry about finding the second derivatives for e's or fractions on the test for the concavity. So find the critical numbers. To find the critical numbers for a second derivative, the second derivative here is a fraction. I'm going to separately set the numerator and the denominator equal to 0. When I set the numerator equal to 0, it doesn't have an x. I don't get a critical number. When I set the denominator equal to 0, it's enough just to set the inside of the parentheses equal to 0. Subtract 1 and get x equal -1 for my critical number. So this graph is going to, well, my work is going to have me put the number negative and positive infinity on a number line along with the critical number of -1, which is actually where an asymptote is. -1's not in the domain of the original function. If I plug -1 in, I'll get a 0. The graph isn't continuous. It actually has a vertical asymptote there. For the first interval, I'm going to plug in -2. For the second interval, I'm going to plug in 0. And I'm going to use that derivative. I'm going to evaluate the second derivative at -2, which is going to be 10 over -2 plus 1 cubed. And then I'm going to evaluate the second derivative at 0 and do 10 over 0 plus 1 cubed. This is going to be -10. I could do this on my calculator, but that I can do in my head. This is going to be +10. You can do it on your calculator if you can't do it in your head. This first region is concave down. The second region is concave up. So when I answer 24A, it's concave up in the interval from -1 to infinity. When I answer 24B, it's concave down in the interval from -infinity to -1. When I answer 24C, even though the graph changes from concave up to concave down, right here, there's a vertical asymptote as opposed to a hole because the denominator doesn't cancel with the numerator, and you can't get an inflection point where a vertical asymptote is. That part's not part of the domain. So in terms of the inflection point, there's none. And I'll show you this graph just so you could see the graph of 5 over x plus 1. If I graph the function 5 divided by x plus 1, zoom standard because I don't know what window I was messing with. The first region from -infinity to -1, there's the concave down. Have my vertical asymptote at -1. Then the region from -1 to infinity, it's concave up. I can kind of get my calculator to show a vertical asymptote if I just take 1,000 and multiply it by the denominator so you can see that vertical asymptote. So concave down to the left of the vertical asymptote, concave up to the right of the vertical asymptote. At the vertical asymptote, you can't get an inflection point, so this doesn't have an inflection point. All right, 3,4 is essentially 3,1 and 3,3 put together, where we find maximum and minimum values, increasing and decreasing intervals, concave up and concave down integrals, inflection points, and we find x-intercepts, y-intercepts, and asymptotes, and we full out sketch graphs. So the calculus part is sections 3.1 and 3.3, and then we take some stuff from college algebra, because in college algebra we graph and we find x-intercepts and y-intercepts, we find vertical and horizontal asymptotes. So it's all of what we did in section 3.1 and 3.3, along with stuff that we've done in college algebra that you might have forgotten now that we'll review. But there's nothing that you haven't seen before in section 3.4. It's just putting a bunch of stuff together in some really long problems.